Howdy, howdy. This is Mr. Potter. In our last video, we talked about how to use the merge sort, a recursive sort, to sort through a list of our fraction objects. So what I want to do today is I want to talk about one other type of recursive sort, and this sort is called QuickSort. So the first thing I want to do is I kind of want to illustrate the idea behind it. What we're going to be doing is, if I have a list of numbers like 1, 2, 3, 4, 5, 6, 7, 8, this list of numbers has a property that if I choose some number here, like 5, every number before it is actually less than it, and every number that's after it is greater than it. And that's a property of all sorted numbers. So if I take this list of numbers and I jumble it up, 1, 7, 3, 8, 2, 6, 4, and 5, for example. Then what I want to do is I want to take this list and I kind of want to break it up so that I have some point in the middle where everything to the left is less than it, and everything to the right is greater than it. And if I can get that true, then all I have to do is sort the front part of the list and sort the back part of the list, and I'll have a sorted list. And of course, it runs on the same divide and conquer idea that we used with merge sort. So I know this is index 0. I know this is index 7. And if I take 0 plus 7 and divide by 2, I get 3. So here's position 0, 1, 2, 3. Now, what I want is I want all the numbers that are less than 8 to be on this side. And I want all the numbers that are greater than 8 to be on this side. And I've chosen this as an example to show what a bad scenario might be. So is 1 less than 8? Yes. So what I'm doing is I'm actually keeping track of the front of my list and the back of my list. And I want to try and get it so that these two fronts and backs narrow together to a point. That's the idea here. So if front is less than, here we'll just call this my pivot, because this is where everything kind of balances at. If this is truly less than 8, then I'll go ahead and advance f to the next. 7 is less than 8. 3 is less than 8. 8 is not less than 8. And so I don't want to advance f any farther forward. So here's b. Is b greater than 8? Because remember, I want all the numbers on this side to be greater than 8. And that's not true either. So what I've done is I've reached the first point where the front of this front pointer is pointing to something that's not less than my pivot. And this back pointer is pointing to something that's not greater than my pivot. So I want to swap these values. So I want to swap the 8 for a 5. But keep in mind, my pivot has changed as well. I'm still looking at 8 as my pivot. So then I look at this and I say, okay, is 5 less than 8? Well, sure it is. How about 2? Is 2 less than 8? How about 6? Is 6 less than 8? How about 4? Is 4 less than 8? And this advances all the way until I reach this point where I'm dealing with 8 being both the front and the back. And since we're now talking about the same location, this is my pivot, and I know that this value here is sorted. Now again, this is a bad scenario, but now that I know that is sorted, I'm now looking at the index from 0 to 6. So again, I'm looking at position 3. This is my pivot again. And I'm taking track of the front of my list. I'm also keeping track of the back of my list. And I want to continue that same algorithm as before. 1 is less than 5, but 7 is not. 4 is not greater than 5, so I want to swap. So this becomes the 7, and this becomes the 4. Now, 4 is less than 5. 3 is less than 5, but 5 is not less than 5. 7 is greater than 5. 6 is greater than 5, but 2 is not greater than 5. So I want to swap. So this becomes the 5, and this becomes the 2, and of course my pivot has moved. And now I do this again. My front 2 is less than 5, but when I advance to here, 5 is not less than 5, and 5 is not greater than 5. So now I've reached this scenario where everything to the left is less than 5, and everything to the right is greater than 5. Now keep in mind, I know this 8 is sorted, so I really don't have to check that anymore. But what I want to do now is I do want to sort the front half of the list, and then sort this back half of the list, and then my whole list will be sorted. So here's position 0. Okay, but I actually know for a fact that this 5 is in the right spot, because everything less than it, everything before it comes less than it, and everything that comes after it is greater than it. is position 0, this is position 3, so my pivot is at position 1. And so this is going to be the front of my list, and this is going to be the back of my list. 1 is in the correct spot, but 4 is not. 2 is not, and so these are going to swap. So this becomes 4, this becomes 2, and this is now my pivot. But 2 is less than 4, 3 is less than 4, 4 is less than 4. So I know that everything here is sorted. And it's this idea that I'm going to find a pivot, sort everything to the left, sort everything to the right. Find a new pivot, sort everything to the left, sort everything to the right. And eventually my entire list will be sorted. So let's talk about how we're going to code this, writing the code for this. So the first thing that I want to do is I have to keep track of the left and right ends. That's probably the most important part in deciding this partition. I'm going to have to find a pivot, which probably the most straightforward thing to do would just be to select the number that's in the middle of that little sub-array. And then I want to essentially QuickSort the left part of the array, and then I want to QuickSort the right part of the array. And of course, what we've noticed is that the actual recursive part is going to be very easy to code, fairly straightforward. The hard part is this idea of dividing and conquer. That's the hard part. How to actually figure out how to partition the list. So let's go ahead and talk about how to do this. So I'm going to have public static int partition, and I'm going to have some fraction array, which I'm going to call list. I'm going to have some starting position, and I'm going to have some ending position. And what I want to do here is I want to keep track of the left and right ends of the array. So let's go ahead and call int front gets start and back gets end. The idea is that I want to keep track of the front and back, these positions that are going to move. But I really don't want to change these starting and ending because they're really the bounds of my array, or at least the part of the array that I'm interested in sorting. So I've got a front and I've got a back. I need some temp fraction that I'm going to be keeping track of. And I'm also going to have some fraction called called pivot, which is going to be wherever that middle element of our list is. So list sub front plus back divided by 2. And of course, this is the one that we want to get so that everything before it is less than it, and everything that's greater than it comes after it. So now I want to set up a loop. So while front is less than or equal to back, because eventually I want this front and back to meet in the middle. They're going to meet at our pivot, and I can return either of these values when I'm done. So while this is true, I want to check the front. First, I want to check the front of the list. So while list sub front, and I really want to say less than pivot, but I can't do that because these are objects. I have to use that dot compare to method that we talked about when we created our fraction class. So when I compare it to pivot, I want something that's less than 0. In other words, this object should come in front of the pivot. And as long as this is true, then that number's in its proper space. That fraction's where it belongs, and so I just want to march towards the pivot. And similarly, while list sub back dot compare to pivot is greater than 0. Can't believe I forgot the 0 there. As long as that's true, then I want to march the back pointer back a spot. And so when I get past when I get to these two while loops, I found elements out of order. So what I need to do is I need to get them in order. But I only want to do that if front is less than or equal to back. Because if I've actually met at the point where front and back have crossed over, then I'm done. But if front and back haven't crossed over yet, then I really need to do this swap. So I need to say temp gets list sub front and list sub front gets list sub back. Semicolons are your friends. And then list sub back gets temp. But the other thing to consider is that once I've made this swap, these two positions are in the right spot. So I really want to say front plus plus and back minus minus. because I know these two spots that I've just swapped, they should now be in the correct spot. And so when I've gotten through this, I wanted to figure out, okay, where is the spot that I'm partitioning? At this point, because I've chosen my pivot at the beginning of this loop, when I get to the end of this loop, both front and back are pointing at that pivot. So all I want to do at this point is just return front, because it's pointing at my pivot. I just need to know where the pivot is so I can partition subsequent parts of my list. So that concludes my partition method. So now what I want to do is I want to write the QuickSort method. This is the recursive part, the part that calls upon itself, and so it should be fairly straightforward to write. So public static void QuickSort, and so I need a fraction array, which I'll call list. I'm going to need a starting position and then ending position. And so what I want to do here is I want to find out, why is that not doing correctly? Okay. So first thing I need to do is figure out, okay, where is this pivot? So int pivot index is going to be equal to whatever the partition is for the list and my start and my end. So this is the place where I need to pivot and subdivide my list. But I only want to quick sort each list if there actually is a list to sort. Remember what we learned in our merge sort, that one element lists are already sorted. So if start is less than pivot index minus 1, in other words, if there's at least two elements to sort in the front half of the list, then we should go ahead and quick sort the front half of the list. So from start to pivot index minus 1. And this is just being problematic today. I'm not sure why. And so if index is less than end, in other words, if I have two elements at the end of my list, then I want to quick sort my list starting at index and going to end. And so this takes care of the idea of the recursion aspect of it. If I have stuff to sort that comes before the pivot, I want to sort it. If I have stuff that I need to sort after the pivot, I want to sort it. And every time I call on QuickSort, I'm subdividing that list, so I'm finding a new pivot. And that new pivot is going to divide each subsequent list into a front half and a back half, which I'll either sort or I'll ignore if there's only one element in the list, which I check for here for the first half, and which I check here for the second half. So all that I really need at this point is like we did with merge sort, I need some type of front end, because the user doesn't care about the start or the end. It's just going to give me a list that I need to sort. So this is actually going to be the public static void QuickSort. And I'm going to overload it so it just has one parameter. Fraction array list. And all that's going to do is that's going to call on QuickSort with the list and with starting position of 0 and an ending position of list dot length minus 1. Now I need that minus 1 there because I only want to sort up to that last index, and the last index of any array is list.length minus 1. And so to make sure that the user doesn't use any of these other methods, I'm going to go ahead and real quick make them private and make this private as well. So let's compile this, make sure I don't have any egregious errors. Just 7,000 of them. So let's go ahead and take care of those real quick. Illegal start of expression, which usually means I have some unbalanced, the issues that I was having at some point, and I hit the insert key and it messed up my automatic braces. So here, oh, it's not index, it's pivot index. And same thing here. So I just need to keep track of that pivot index variable. That works now. So all I need to do at this point, though, is just change the sort. Instead of using merge sort, I want to do QuickSort. And it should do the exact same thing. I've got a list of 100 fractions. The numerators and denominators are going to be up to 20. I'm going to print out a list, sort it, print it out again, and then use the exact same binary search method that we had before. So let's compile this and run it, and hopefully everything works out marvelous. And it looks like it did. Let's check this out. So at the beginning, I had a relatively unsorted, unordered list. And then down here, I've got 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Here's 1/10, 1/7, 3/19, 4/19. So it certainly looks as if this list is sorted. And then down here at this end, I've got 15/3, which is 5, 17/3, which is almost 6. There's 7, there's 9, there's 9.5, there's 12, and there's a couple of 14s. And of course, the number we were looking for, 1/2, shows up in position 21, which 21, let's see, there's 3, 6 right there, and I believe that's the only 1/2 I've got. That's smaller, and that's bigger. So the idea of this QuickSort, this runs a little bit better than merge sort if the numbers are relatively evenly distributed. Of course, I can have worst case scenarios, and one of the things we saw is that when I have that worst case scenario, the sublist that I have to sort afterwards is only one shorter. And so what that means is that if I have 100 elements in my list, I could have my next list be something that's 99 elements, and my next list be something that's 98 elements. I could have a worst case scenario where it actually takes the number of elements squared complication or computations in order to do that. So it's not perfect, and if you have the time to study it, there's actually quite a bit of study of how to choose a good pivot value. I'm just choosing a point in the middle, but there are lots of other ways that you can do it. Some people who try and start at position 0. Some people start at less dot length. There's lots of techniques to do this, but this is just one way to do it. And really, how I find that partition isn't important as long as I make sure that everything before the partition is less than that value, and everything after the partition is greater than that value. That's really the key to a QuickSort implementation. So once again, this is Mr. Potter. Thank you for watching. Have a great day.